Hi, everyone. We're going to spend a few hours or so talking about spray drying. Hope you can endure through it. It can be quite interesting. Anyway, 3 or 4 major sources for this is, or are sources for this. Cook and Dumont with their process drying practice book, and K. Masters drying handbook, this 1985, backed up by Stanley Wallace's book, not this one necessarily, but the other one, the earlier one. And hopefully we have some interesting stuff for you. So then we'll talk about the general aspects of spray drying. Spray drying uses sprays to create large surface areas for drying. It is a continuous one-step particle formation process. Feed solutions and suspensions or pastes in the product are powders, granulars, aggregates. The development of SD spray drying has resulted in a highly competitive process for drying a wide range of products. And I think I took this from the Master's book, a whole bunch of stuff out there. All sorts of areas from mineral to dye stuffs, pesticides. Anyway, a whole bunch of equipment. Different types of equipment involved. And used equipment as well. There's an old broken down spray dryer. Buy it now. $22,000, kind of an interesting statement. Anyway, used equipment. This is a listing of test and toll drying facilities out there. Here, follow up. This list is provided to you by Cook and or Dumont. I'm not quite sure. They probably both worked on it. But S stands for spray. Basically, those are spray dryers, spray dryers, spray dryers, spray dryers. Indirect heating. Capabilities, drying capabilities. Once through, partial recycle, closed cycle, none of these apparently except Y. Rotary tray, go back one. Anyway, nice list, very nice list from Cook and Dumont. Spraying drying, sorry, handles a wide variety of products, meets specifications laid down by diverse industries. Major advantage, few dryers take pumpable liquids and discharge dry particles. Produces a specific particle size and moisture content over the entire range. Continuous, easy, adaptable, full automatic control with fast response times. Wide range of versatile designs available. Applications to heat-sensitive materials. Handles corrosive, abrasive, pumpable stuff. Slurries, paste, melts, solutions. Of course, it's more... This could be a long-term objective. The desire is to have more compact, lower energy-consuming dryers. Lots of specialized subsections in spray drying. Spray freeze drying, spray freeze drying, spray cooling, spray reactions, spray absorption. Anyway, if we take a look at surface area, you're making a use of large surface area for some purpose. If we take 1 cubic meter of liquid and we break it down into drops of 300 microns each, How many drops do we have? Well, we get up to about 7.1 times 10 to the 11th drops. So there's a whole bunch of drops being produced. Then you ask, 1 cubic meter of liquid goes to surface area of those drops. So each of those drops has a surface area, drops having 300 microns in diameter. How much square area is there? 20,000 square meters. So I don't know if you appreciate that. There's a whole bunch of area, all fairly uniform, seeing approximately the same environment. The 300 microns eliminates diffusion as a drying limitation. You have such huge area. Diffusion's a pain in the neck, okay? You don't want to be diffusion controlled because it usually means long processing times. Diffusion's acting, of course, everywhere all the time, but you don't want it to control. So the way you do that, you have it large surface areas. Disadvantages for spray drying: high fabrication costs, high installation costs, need supported medium structures in buildings since units are physically larger. SD is convection dryer, has poor thermal efficiencies, 20–30%. Large amounts of, that's efficiency, 20–30% efficient. Large amounts of low-grade waste heat may require expensive heat exchange equipment, which handles powder-laden air at saturated or near saturated conditions. Low inlet temperatures of 300 degrees centigrade. Typically, you want inlet temperature to a dryer is set by the temperature at which material starts to degrade on you. Temperatures at which you have product degradation. Typically, you're shooting for the highest. Applications go to the extreme, from the most delicate conditions of food and pharma to high tonnage for bulk chemicals or heavy chemicals. So what's involved? Well, it's like, I should point out that there's a video out there on direct drying. You should review that. So that would take care of explaining this heating and gas. Then there's a video out there on atomization. You should review that. So spray drying involves heating a gas, exposing it to liquid, which is the atomization. Combining 1 and 2 heat and liquid drops, moisture is removed from the solid. Moisture is picked up by the gas or by the air. So you have the sensible heat, the moisture in the air picks up the moisture that's lost from the solids. Atomization is usually done with nozzles or rotary atomizers. You can also have 2 fluid atomizers as well. Nozzles use pressure drop. Rotary atomizers use centrifugal energy. Nozzles, wide range of sizes and designs, typically are for lower flow rates than rotary atomizers. If you're going to high flow rates, you're going to have duplication. You're going to have many nozzles, so to speak. Also, the nozzles are not, unless you have nozzles that have a turn-down ratio, most nozzles are for a fixed flow, fixed pressure drop. Of course, there's nozzles out there that have turn-down ratio. Turn-down ratio is maximum flow rate to minimum flow rate, 1 to 10, 10 to 1, or I can go to 1 to 40 or 1 to 50 with some of the more complicated designs. Rotary atomizers' wheels are fed centrally. Low pressure operations, major variables, feed rate, rotational speed, and geometry. Those are the fundamental. You have the material properties, you have the operating conditions, and you have the geometry. Three of the fundamental variables of process design. Wide range of spray characteristics. Wheels handle very high flow rates. Vanes on the wheels are high, wide, straight, or curved. Bushings are, we'll show you bushings later. They're circular or square. Bushings are used to handle abrasive feeds. Bushings are, there's holes in spray dryer wheels. And spray dryer wheels are very expensive, and bushings are added to the holes to have them as the items that wear. And then when they wear through, they're near that condition, they're exchanged for newer ones. Discs include vane plates, cups, and inverted bowls. Discs are used to meet coarse spray requirements. Again, I highly recommend my course on atomization, or excuse me, my videos on atomization. Rotaries are reliable, easy to operate, handles fluctuating feed rates, high feed rates without duplication, handles abrasive feeds. Particle size is controlled by wheel speed. Rotary atomizers produce particles around 30 to 120 microns. Nozzles have coarser particles, around 120 to 150 microns. Pressure controls feed rate, spray characteristics, and particle size. Pressures are very high. Can be very high. Okay, so that means you gotta have a source for high pressure. Two fluid nozzles are for, there's three main ways: rotary, nozzle, and two fluid atomizers. Basically, you use a second fluid to blow apart a high viscosity material, typically. So two fluid nozzles, if you get to too high of viscosity, are used. If the material you're trying to atomize is high in viscosity, you go to two fluids, producing medium coarseness. In which case, with two fluid atomizers, the important variable, one of the important variables, is the air to liquid ratio or the gas to liquid ratio. It's a ratio of mass flow rates. Although I would have a tendency to want to talk about momentum flow rates, typically the literature is focused on mass flow rates. Atomizer selection depends upon the nature of the feed, design characteristics of the dry product. Increasing power input always decreases particle size. For any engineering operation, you always need to pay attention to power input. And if you don't know how to calculate power input, then you should spend some time in figuring out how to do it. So increasing power input decreases particle size. Increasing flow rate at the same power increases particle size. Higher viscosities, higher surface tension results in larger particles. Now, higher viscosities are taken care of with the OSOG number discussed in my atomization course. High surface tension is taken care of in the Weber number. So these are two-dimensionalist groups that you need to find out about. There's an excellent video, I think, on OSOG number. Let me spell that for you. OHSORGE, I think. I'm sure I'm brutalizing it, the name, but video shows different values of that dimensionless group, how a breakage occurs. Two major resistances or factors in drop breakage or formation of drops, is high viscosity. Fluids doesn't want to move, basically. And the other one is surface tension. If you have a high surface tension, then the drop will be round, very, very round. And essentially, under both of these conditions, you will have a very strong, unbreakable particle or drop. Anyway. Rotary atomizers have great flexibility and ease of operation, often selected over nozzles. Right? Spray contacting drying air. This is one of the important things why you talk to a spray dryer company. Okay. And typically, atomization is pretty well understood, and the drying is pretty well understood. The mystery is the airflow rates and how they're distributed in the dryer. Now, that's why you talk to a spray. There's a number of reasons why you talk to a spray dryer company, right? However, one of them is how the air is circulated in their dryers. Determine the position of the atomizer relative in relation to the drying air. An important factor in SD design. Has a great effect on dry products. Many positions are possible. Contacting is either co-current, countercurrent, or mixed. So here I've lifted this. I'm not sure from Stanley's book. I'm not sure where it's figure. Anyway, co-current, countercurrent, mixed current. What we have is F for feed, G for gas. So we have feed coming at 40 degrees. Okay. And hits hot air, right, or hot gas. So we have low temperature liquid hitting high temperature gas, and it circulates around. I suspect this is gas temperatures, perhaps. Feed comes in at 20 degrees, sorry. Product particles leave at 90 degrees, and I guess these are degrees centigrade. And gas leaves at 120. So the gas essentially, as it picks up moisture, it drops in temperature. So the sensible heat of gas goes into evaporating the liquid, and the liquid heats up a bit. So the liquid material comes in at 20, and eventually the particle leaves at 90 degrees C. And this would be co-current operations. Here we have also co-current operations. Here we have countercurrent operations. Here, I guess you can say that the highest temperature gas meets the highest temperature particles. And again, you can see the gas cooling down as it picks up moisture. And you can see the feed heating up and leaves as part of it leaves as particles at 120. So this is countercurrent. And then we have some sort of mixed flow where there would be a fountain arrangement from this feed. Okay. Gas comes in at 450, leaves at 125, and particles leave at 95 to 100. You can see the particle 90, 95, 100. Then you have one higher than that. Countercurrent operations, again, the product sees as it leaves, it sees the highest temperature gas and countercurrent. We also have what might be referred to as protective cooling going on. So as the feed comes in at 20 degrees, it's evaporating away, and it's not heating up, okay, as much as you might anticipate, right, because of evaporative cooling going on, right? So here we have a large temperature difference, but little product degradation going on. So I want you to do an experiment for me. It's pretty simple. I want you to take a shower. It's pretty simple. And as the hot water comes out, it's probably, I don't know, 120 Fahrenheit. Put your hand up around the shower header and feel how hot it is. Then drop your hand down further on down to your shoulder and see how much cooler it is. And as the drop comes out of the shower header, it's hot, but evaporative cools by the time it reaches your body. That's an example of evaporative cooling. Another example is in the cooking of French fries. I mean, if you put French fries in hot oil, and the hot oil is 300 degrees centigrade, say, or 200 degrees centigrade, much hotter than boiling, you'll notice that the French fry bubbles. And the question is pretty simple. What's causing the French fry to bubble like that? And second is, what's the temperature of the French fry? Even though the hot oil is 200 C, the French fry is actually most likely at 100 degrees C, because the boiling that's occurring around that French fry is water evaporating off, and the water boils at 100 degrees C. So when a French fry is sitting in hot oil, it is 100 degrees C, no matter what the temperature is of the oil. And it's being protected by evaporative cooling. However, after a while, a lot of the moisture leaves the French fry, okay, and it heats up. And as it heats up, the French fries turn brown. So the same sort of principle happens. There's a lot of protection due to the liquid being boiled off, or evaporative cooling, keeping it cool. Out west, they have, in the hot Arizona area, they have humidifiers outside on their patios. They spray a fine mist of water, and as the water evaporates, increasing the humidity, of course, it lowers the surrounding air temperature. The same sort of thing happens here. And they give you an appreciation for the temperature distributions and a spray dryer. So if we take a look, feed may be similar to boiling liquid drops, boiling liquid foam. Boiling foam, an example, I want you to go and watch these 3 videos on YouTube. If you haven't realized it or not, YouTube's extremely powerful. Videos on YouTube are extremely powerful in the education. I wouldn't be a bit surprised if somehow factors into education in the future. But so many people have put so much fantastic stuff on YouTube. It's unbelievable. So making molasses, I want you to watch how molasses happening. So sustainable sweetness. Anyway, I want you to sit down and take these and go watch them boil molasses down. And my thought is there's similarity to boiling down molasses, which thickens the molasses, right, to the liquid drops floating around in your spray dryer. The boiling that takes place in these molasses is very similar to liquid drops boiling. So I'll give you an idea of transposition, so to speak. The physics are the same. It happens 2 different locations. Co-current operations, spray is directed into hot air entering. By air, I mean gas. Okay, product and air passes through the dryer in the same direction, widely used for heat-sensitive materials. Okay, it's heat-sensitive materials because, again, you have evaporative cooling going on. Protects the product. Evaporation times are short. Product is not subject to heat degradation. Product temperature is low due to evaporation, evaporative cooling again. Drop temperature approaches wet bulb temperature. Air becomes much colder, much cooler. Lower temperature conditions are in almost the entire chamber. Okay. Radial trajectories of the rotary atomizer can be controlled to prevent excessive deposits on the spraying chamber, drying chamber. You can control spray angles. Spray angle is often given in all sorts of technical information, but just as a single operating without any confinement or whatever, there's a spray angle there. And for a wheel, it's 360 degrees flat, right? But you can bend that, believe it or not, by airflow rate and baffling. You can bend a horizontal spray into a shape of an umbrella, if you like. It takes talent, or it takes understanding, but it would be a good way of understanding flow in your spray dryer chamber. In fact, I would go so far as to say you ought to build a model. Build a very small scale model. Say you have a dryer 10 feet in diameter, 20 feet in diameter. So you build a model of it at 1 foot in diameter. And you put in the baffling or gates or vanes on how you are going to control the air. If you can control it that way in a small scale model, you could possibly control it in large scale model. It'd be quite an adventure for you to do that. Okay, counter current. A spray and air enters at the opposite ends of the dryer. Excellent heat utilization. However, it subjects the driest particle to the hottest airstream. Right there's your product deterioration problem. Heat sensitivity meets requirements of non-heat sensitive products. Upward stream of air reduces particles' fall velocity. Upper stream of air increases the residence time in the chamber needed for complete evaporation. Mixed flow incorporates both counter and co-current. Powder is subjected to higher particle temperatures. Of course, free-flowing powders can be produced in small chambers. Okay, airflow rate predetermines rate and degree of evaporation. The influences the passage of spray through the drying chamber. As I said, you can bend the airflow rate, can bend the spray angles, expand them out, reduce them both. Influence the concentration of particles along the dryer wall, influences the extent to which semi-dry particles re-enter the hot areas around the air disperser. Product determines how best to contact the air and the spray. Countercurrent, hottest air contacts driest particles. Best suited for coarse, high bulk density particles that can withstand very hot environments. Low porosity due to reduced tendency to expand rapidly. Right? Fracture, evaporation, and fracture during evaporation. So when the particle eventually sees the hottest air, right, that means somewhere the wettest particle sees the coolest air. So it reduces rapid evaporation and hence lower porosity. Okay, so this countercurrent means lower porosity. Highest co-current, highest air contacts droplets at their maximum moisture content, best suited for materials that can't withstand high temperatures. Rapid evaporation prevents high droplet temperatures. Rapid evaporation may expand or fracture to give a non-spherical porous particle. Again, this is a boiling molasses syndrome here, or similarity. And because boiling molasses, if it was to be frozen, would be a low bulk density. Bulk density is, of course, a concern. Okay, chamber design and air introduced. Well, let's try it again. We probably are saying similar things as we did earlier. Here's the example. This is co-current. They're going in the same direction. This is co-current. This is countercurrent. And this is mixed. Give you an idea what they are. The drying chamber and air introduction selected according to the required particle size, required particle form, porous or non-porous, temperature to which the dry particle can be subjected. Lots of choices. Co-current used for fine products, 30 to 120 microns with low product temperatures at all times, lower than the outlet gas by, say, 25 degrees. Co-current pressure, this is rotary up here. Co-current pressure nozzle towers used for coarse products with low temperatures. Okay. Countercurrent used for coarse products, high product temperature for heat treatment. Right. Obviously, you have heat sensitive materials, but then just on the opposite of that, you have some materials that require heat treating. High product temperature for heat treatment. Instead of heat sensitivity where you ruin the product, you actually are trying to heat treat the product. For special porosities, bulk densities, or case hardening effects. In my dryer course or video, direct drying video, I give a listing of all the different ways material can be damaged during drying and the case hardening effect. There's a lot of other things that can happen to material as well besides case hardening. Mixed flow used for coarse product with low product temperatures. Product is not so heat sensitive and can tolerate some heat treatment. Dryers of limited size and volume. Okay. Drying of individual particles. Evaporation takes place from a saturated vapor film at the particle surface. Well, maybe yes, maybe no. Of course, there's some sort of vapor film coming right out of liquid, but whether it is there's some sort of vapor coming out of liquid where it forms a film or not is another question. If it's a bubbling surface with lots of surface renewal happening around it, I'm not sure that's an important issue. So basically both can happen, right? There's very little film formed or there's a whole bunch of film formed. I suspect that very little film is formed. Temperature approaches wet bulb temperature, two-stage. You have constant rate drying or constant falling rate drying. Constant rate, plenty of liquid around for evaporation and maintaining saturated conditions. Liquid may diffuse to the surface. Not enough liquid. Falling rate to maintain saturated condition. Evaporation depends upon the state of the rate of liquid through the dried surface shell. Thickness of the dried surface shell increases with time, which decreases the evaporation rate. Some wills, by the way, produce liquid sheets and also ligaments. So the focus on drops is well-deserved, but you also got to recognize that liquid sheets are being created as well. Substantial part of, well, the liquid sheets eventually break down into drops. Drops then go to particles. I'm particularly interested in knowing how particle size, or if you're drying something that has a particle size contained in it, like you're drying a slurry, how the particle size affects the atomization, which then affects the drying. Because I can envision y'all trying to dry a slurry of needles, and that behavior, the needle length could have a profound effect on size of the particle. And other of the more interesting particle shapes, like if you're drying flakes, how would that slurry made up of flakes or slimes, how would that happen? Substantial part of the evaporation takes place when surfaces are saturated and cooled. Drying chamber and airflow provides the residence time for removal of the desired amount of moisture. Product leaves the dryer before any significant temperature rise can occur, which would cause heat damage. Well, I bet you there is a whole bunch of material in there that basically wall buildup, for example, will stay there and experience heat damage. One of the reasons why you don't want to use a spray dryer is you have wall buildup. As a result, wall buildup, you can have the material stay in there for long times and hence ruin the. Occasionally, it would drop off the wall and enter your product stream. So this is it's what you're looking for here. Product leaves the dryer before any significant temperature rise. It's what you're looking for. It doesn't necessarily mean that's what you get. Particle size distribution. Distribution undergoes significant change during drying. Different products exhibit different evaporation characteristics. Some expand or collapse, some fracture, some disintegrate. Particles become porous, irregularly shaped, others become spherically shaped and dense. Change of particle shape and dry characteristics are closely related to drying rate. Anyway, so let's take a look. The relationship between drop size and particle size. Drop size, again, my atomization course, you have a number of reliable correlations on how to predict drop size. And the question is, I have a certain drop size and I have the moisture ratios, right? Moisture to solid ratios for wet conditions and dry conditions. I use a small w for moisture to solids, capital W for wet, anyway, and D for dry conditions. So one of the neat things about solids weight, it's constant. For the particle, it's a constant. Right. The moisture is what's changing the weight of the particle. So we have the weight fraction defined as this. And if we take solid weight, divide it through top and bottom, we have this equation. So we have 1 over 1 plus W. And typically, you know what moisture to solid ratio, wet, and the moisture to solid ratio, dried. What you have coming in is feed, you know that. And typically, you know what you want to dry down to. This is weight percent at the beginning and end of drying. So we can have this relationship. Initial solids content in the drop is, if you work out the units, I have the volume times the density times the weight fraction, right? I have the finals concentration. This is the wet density. This is the dry density. I have the particle diameter dry, and I have the particle diameter wet. I have wet moisture fraction. I have dry moisture fraction. These two equations, 1 and 2, are equal to each other. And the only thing I don't know is the ratio dW to dd, which I do these substitutions in, take the cube root, and I got a relationship between the diameter of the drop, or the diameter of a D being dry, right? Go back. Subscript D. D's for dry, W's for wet. Come back here. Oops, sorry. D's for dry, D's for wet. I know all these variables here, so I can calculate, give you a sample calculation here. Typically, I am looking at wet, maybe 1,300 kilograms per cubic meter, 50-50 moisture, right? Or WW, whatever that definition was. Drying down to 0.08, substitute in, calculate. I quickly find that wet diameter to dry diameter, I have this dry diameter is 0.65, wet diameter. So a 100 micron drop goes to 65 micron drop. Of course, this calculation assumes no breakage and assumes round spheres. No breakage, right? Where do I cite those? I don't cite those. But anyway, this calculation is sort of an idealistic calculation because you will have particle attrition or particle breakage, attrition being breakage. Another word for breakage. Anyway, so it's kind of interesting that you can sit there and calculate dry particle size to wet drop size. And if you characterize your wet drop size, then you can get the idea of dry particle size. However, again, highly idealistic, right? Just as a guide, give you a better feel for your spray dryer. Two ways of handling solids, right? Particle discharge. One, you have the atomization drying chamber. The product falls out the bottom and cone bottom. And air and entrained power goes out through a cyclone, and you have secondary discharge. Now, this means there's two discharges, which increases the complexity. And this, you have everything goes out the bottom, goes to cyclone. Total particle discharge from one point, air goes out. So you have two methods. Primary separation takes place at the base of the drying chamber. Majority of products fall to the base. Small fraction of entrained in air and captured by a cyclone. Cyclones are dry collectors and followed by wet scrubbers. Okay. Alternative dry collectors are bag houses or bag filters, electrostatic precipitators. I don't know, bag filters, you have a vacuum sweeper at home. That's a bag filter. You got the dry particles off your carpet going up probably in a cyclone. Some of the operations involve cyclones, very visual, to collect up stuff. Choice of equipment depends upon powder loading of the air leaving the drying chamber. And you're looking for acceptable efficiencies of recovery. Classification occurs. In this operation, classification occurs. Some of the large heavy particles are over here and the fines are over here. Whereas over here, they're all clumped together. Plus, the large particles will experience attrition going in this line. So your chances of increasing fines production is higher in this design. Less fines here, and you already have them separated, or I should say partially separated. Now this air should go through perhaps another cyclone. There's nothing wrong with staging cyclones. Or a nest of cyclones, perhaps then electrostatic precipitator, a scrubber, or a bag house. And then eventually, if the solids concentrations are still there or something nasty is still there, you burn it. So I don't... I said classification occurs. This form of classification is sometimes useful. Normally, the two powders are combined and conveyed to the discharge area. Okay. Second method, recovery takes place in equipment. Separation equipment places great importance on separation efficiency, often used because it doesn't need product conveying system. Okay. Separation of dry product from air affects powder properties because of mechanical handling. Okay. Excessive mechanical handling can produce powders with very high percentage of fines. So, Okay, let's start and talk about types of spray drying. You have open cycle, closed cycle, self-inertizing cycles, and other cycles as well as we come up with. Open cycle, hot air in, air dries, air exits the atmosphere. Closed cycle, well, the problem with open cycle is you have oxygen, for one thing, in there. Oxygen causes dryer fires, oxygen causes product degradation. Oxygen is not necessarily desirable. So then you run in a nitrogen atmosphere. Basically, you have nitrogen coming in, nitrogen dries, nitrogen recycles. Inert gases prevents the risks of explosions. Organic solvents are evaporated and recovered as well. So if you're going to run with solvents, then you probably want to run inert or closed cycle with inert gas. Self-inertizing cycles, basically you start with oxygen and then over operational time it's reduced below 6%. And this is by controlling the amount of excess combustion air into the direct heaters. So self-inertizing, this eventually remove the oxygen, and as a result you approach inert conditions. So here's a listing of those: open cycle, closed cycle. Then you have semi-closed, partial recycle, semi-closed sort of standard, semi-closed. Self-inertizing, drying is air, inert gas, air with low oxygen. Heating is direct. You have indirect dry heating here. By direct heating, basically the hot gases are added directly to the spray. There's no wall in contact. This is if you have a wall in contact, that just adds another resistance to heat transfer. Efficiency goes up really high when you have direct, or higher when you have direct. And applications, you have the developed for, an old idea now, developed for thermal efficiency. Okay. Used to be a long time ago, or I shouldn't say a long time ago, natural gas was expensive. Now natural gas is very cheap. A few years ago, we had an energy crisis. Now we don't have an energy crisis. 10 years ago, there was a great emphasis on energy savings and spray drying. That may still take place, but it seems to be not nearly as urgent as it once was. Semi-closed, only a fraction of air bleeds to the atmosphere. This occurs in standard design, partial recycle. Two-stage or multi-stage designs, special designs, aseptic, special cooling systems, lines return. So let's take a look at an open design. Again, open cycle layouts, feed comes in, the air comes in. A is the air, M1 is the spray chamber, product out the bottom. The air passes through, the exit air passes through a bank of cyclones perhaps, or electrostatic precipitators, passes through a bag house. They all should first pass through a cyclone. Cyclones are so cheap. Maybe a wet scrubber. Cyclone scrubber, most common, cheapest, high efficiency. Particulate loss can be closely controlled. Particulate loss can be closely controlled. 25 milligrams per cubic meter. Often cyclones can't be used for high abrasive materials. Bag houses use very fine particles are produced. When particles are too small to be removed from cyclone scrubbers, used when atmospheric emissions must be negligible at 10 milligrams per cubic meter. Used when the product is very friable and collection requires minimum mechanical treatment. Herbicides and pigments are examples. May need a backup wet scrubber for bag ruptures. If we have a bag sitting here, right, and it becomes loaded or heavy loading on it, pull of gravity may cause it to rip, and a little hole goes, and as a result, air exits through that hole, bypasses the filtration. Anyway, so bag houses 10 milligrams per cubic meter. Okay. Electrostatic precipitators used for high gas flow rates or low pressure drops while maintaining collection efficiencies. Established layout in the mining industries. Used when cyclones can't. Well, used when wet scrubbers can't due to water shortages. Many mining locations have no water. All our processing is geared to an ample amount of water, and if you don't have ample amounts of water, processing has to be changed. Closed cycle, based upon recycling and reusing the gas medium, inert gas like nitrogen used for new products, help solve problems with conventional methods. Uses an airtight design operating at low pressure above atmosphere, so it leaks out. Particularly useful for flammable solvents, complete solvent recovery whenever you're drying toxic materials. Anyway, it looks like this. First thing you want to note is 3 is indirect heater, basically. This is a heat exchanger. Okay, there's 3 major types of heat exchangers, right? Shell and tube, plate heat exchanger, and a spiral. Spiral is really nice exchanger for low pressures. Under both plate and spiral heat exchangers are useful under 300. Is it 300 psi? Yeah, under 300 psi. So we have indirect heat exchanger. There's a wall here between the heating and the cooling. So you want to heat this up. You want to heat this stream up. So this is the heater. Liquid phase, indirect heater, heats this gas phase up, hits the feed. Feed separates into particles at the bottom, goes to a cyclone. Then it goes to a wet scrubber, also a condenser, right? Because you want to take the air back. You want to remove the concentrated material here, take the gas phase back to the original entry point, and we'll show you that a little later, probably in part 2 if I do have a part 2. So the feed comes in, separates out in a product, and the liquid comes out over here. Okay. So you may have 2 product streams, one coarser, one fines. Then I'm not convinced that everything got out with this wet scrubber condenser here. It's a condenser to take it material back to the original input, but also a scrubber. So this liquid may actually contain solids in it. And this may require some sort of filtration involved, which brings up my other short course or videos on filtration 1 and 2. Here we have a cooling operate this condenser. Look, we got relatively hot gases. We may not want to cool it, but it may help us to cool it. But then we come up here and reheat it. So anyway, there are other ways of heating this stream other than an indirect heater. See what we got. Closed cycle, reasons for it. Absolutely no atmospheric pollution is permitted. Explosion fires mixtures can form with air. That's why you enclosed with inerts. Explosion fire risks with organic solvents. And then possibly if you had oxygen in contact with your product, then you have oxidation effects. So your designs are airtight, high efficiency product recovery, either cyclones or bag filters. Drying gas recondition, solvent recovery in the scrubber condenser. Solvent recovery, let's go back. It comes in with the feed. See, the feed is solid liquid here, and the liquid is the solvent, and it comes out over here. Nothing comes out up here. Everything, the condenser has an exit up here, and the condenser has an exit down here. You may have some recycle going on here, seems to indicate. So airtight, higher efficiencies, drying air, reconditioning, solvent recovery in the scrubber condenser. Successful closed cycle operations require precise temperature control in scrubber condenser. Usually obtained using available cooling water or brine for high boiling solvents like ethanol. May need a exchanger cooler compressor for cooling low boiling solvents like acetone. Okay. Other features, airtight, operate at slight pressure to prevent any inward leakage of air from outside. So if it's going to leak, it's going to leak from the inside out. This differs from open cycle, which operates under a slight vacuum where stuff from the outside can come on in. Questions? We'll skip the questions. Other closed cycle, we have semi-closed cycle, self-inertizing, pharma and two-stage system layouts. The pharma stuff can be quite complicated. Okay, semi-closed, obviously it's a cross between open and closed. It's not airtight, operates under a slight vacuum. You have two major types, partial drying medium recycle, major drying medium recycle. Partial drying adopted to utilize waste heat and exhaust air. Although I was saying natural gas is not very expensive these days. I think it dropped by a factor of 10. This is now February 24th, 2020, so natural gas is really cheap. However, you know, a utility bill is a utility bill, and it can be quite high, even though natural gas is cheap. So you may wish to adopt it to utilize waste heat and reduce fuel dryer. Let's see what we got here. Now, this would be a partial recycle. That means you have the spray dryer, dry collector, making your product. Now, dry collector may be cyclone. Then it splits here. Some of it's fed back. This is a hot stream, still hot. So it's fed back, and then you put in waste heat. And what bothers me is this waste gas, because if I put in waste gas, I get waste gas back out. So you want to put in, if waste gas doesn't come out over here, then it accumulates in there. And not a great idea. Unless, of course, this is a direct burner where you're burning it. So you have fuel and combustion air coming in. Now then, if you have a burner in here, that's fine. That way you can burn that waste gas or the waste in that gas. But you do the split up here and recycle. This is a hot stream, and that stream puts a less of a load on the burner, right? and saves you money. And the hot stream also then goes to the condenser and discharges to the atmosphere. But I don't want that waste heat to come out of the heater. I want it burnt in there. Down here we have a majority recycle. Okay. Again, from the direct scrubber goes to the scrubber, which then goes to recycle to the heater. So we could potentially have solids coming, a very fine amount of solids coming out of this condenser. Of course, we're losing a lot of the heat here, right? We did heat recovery here, some, but since all this goes to the scrubber condenser, it would be a cooling system, take the heat out. Of course, if I take the heat out of my wet scrubber, right, here I have the cooling going on. So this is C, which would be what? Coolant. I heat up my coolant, which could potentially go to heating up my feed, right? So a little bit of pinch technology there where you're matching heating and cooling requirements with different streams. If you haven't tried or thought up pinch technology, it's applied to a single spray dryer unit, would probably be advantageous to you. Okay, let's see what we got. Partial drying, we already talked about that. Well, let's see, recycle depends upon water content in the dry air going to the drying chamber. Okay. Depends upon the required outlet temperature to maintain the desired residual moisture. Up to 50% of exhaust gas can be recycled in most cases, where the outlet temperatures are above 120 C. Has led to a 20% reduction in fuel consumption. That's your utility bill, especially if the outlet temperatures are high. Allows the use of a smaller scrubber for cleaning, a smaller amount of gas. See, if some of the gas goes this way, you don't have to clean it, right? It reduces your scrubber operation requirements and lowers the cost of the scrubbing action. Open cycle designs can be built to partial recycle designs. So you have an open cycle, there's not much you have to do here, right? Basically, open cycle, if we take a look, open cycle, this line was not there. So that's open cycle, bam. Now, a closed cycle or semi-partial recycle, you have this line here. That's all there is. So open cycle designs can be rebuilt fairly easily. Major dry immediate recycle, two distinct uses depending upon direct or indirect. The first thing we want to do is take a look at indirect heating. That means we have a heat exchanger. Air is the medium, standard drying components are used, the plant is not airtight. Amount of the air vented equals the amount of air entering due to leakage or direct air injection. Direct air injection becomes part of the combustion air, operates under a slight vacuum. So let's take a look at this beast. So all we're doing here is, what are we doing? We have the standard, pretty much the standard here. This is essentially open cycle. Then we add in the fuel comes in and air comes in and gets put into a combustion chamber and is burnt separately than this stream 3. It's indirect, so there's a wall here between these two streams in this heat exchanger. Right. Now the kicker is hopefully the scrubber condenser has removed most of the particulate, right? But maybe some of it hasn't been removed. So then you bleed a stream into here, which will burn off, let you burn off that material. So you have the fuel and air coming in, you have cooling coming in here. Okay, you have the liquid condensed water discharge, which may have particulate in it, which then you need, of course, to filter. So this is kind of indirect heating. Okay. So if we take a look, major majority, medium recycle, indirect heating. We already talked about this. And used for aqueous feedstocks that have odor toxicity problems, but no explosion fire hazards. So the idea of the bleed here, this is a gas bleed, right? First off, you got to realize the gas is all contained here, right? However, the gas may contain obnoxious material, and you may have to bleed some of it off, right? Have a small bleed to the atmosphere, but that has to be exited through combustion. Used when indirect heating is necessary to prevent contact of powder and combustion. Okay. Feedstocks have odor toxicity problems, but no explosion fire risk. Small vent volume containing toxic odor particles is passed through the burner area, and deactivation or deodorizing takes place. Popular choice for herbicide drying. Now, when you have direct heating, right? Direct heating, yeah, that's the limitation here. Well, the inlet temperature may be, this is a heat exchanger, it's less efficient than you would think. As a result, it may limit your capabilities in heating up your inlet temperature here. So if I go to direct heating now, I no longer have a heat exchanger, I have direct heating, heat's added directly. So I can have higher inlet drying temperatures, higher thermal efficiencies, the volume of exhaust gas is lower than partial recycle design. Volume is vented equivalent to volume of production products. Yeah, if complete combustion is obtained, very little excess air is used. The process is self-inertizing. Again, self-inertizing is desirable. So let's take a look at that. We have basically recycle almost once through, recycle, well, not once through, obviously it's not. Semi-closed recycle, you have the standard products. At the bottom, you have the standard liquid, you have the standard cooling. What you have here is the air and fuel coming in, plus the recycled gas. Okay, and hopefully you'll burn down the gas to low oxygen level, which means self-inertizing. You have mainly nitrogen in here. And I kind of worry about this bleed to the atmosphere. I would also have a tendency to put a burner on that to make sure nothing gets out that's bad stuff. The way you get rid of bad stuff is you burn it. Then this liquid may, this bothers me here as well, it may contain a particulate amount of material, which there'll probably be fines. I could potentially have a bag house in here. Or I would put, bag house here would be very, very low concentration material in the exit stream. Anyway, not to have a bag house. The bag houses are expensive and difficult. I would have a burner system there. Self-inertizing systems is used for aqueous feeds when the dry product must not contact air or oxygen, used to prevent the risk of powder explosions or product degradation through oxidation. Ideal for minimizing emissions. The amount of air leaking from the system is much smaller than the amount of drying air. System usually has a direct fired heater, preferably gas, for easy combustion control. Combustion control causes recycled gas to have a low oxygen content. That's what you want. Oxygen is not your friend. Constructed from a standard spray drying compound, it's much cheaper than pure airtight closed systems. No demand for nitrogen or other inert gases. No need for leak-proof system. High inlet temperatures can be used. Good heat economy due to high temperatures. Chamber operates under a slight vacuum. Little chance of the powder blowing out to the atmosphere. Can only be used for aqueous feeds. Obviously, organic solvents need a true close recycle system. Right? Obviously, you can't have this recycle stream. You can't have solvents in this stream here. They'd give a real kicker to your heater, though, wouldn't it? You wouldn't necessarily have solvents could burn off right in there. So it'd be interesting to see if you test that statement. Okay. Organic solvents needed in a true closed system. Used for materials that exhibit undesirable odor generation and or are toxic during drying. Direct venting of exhaust is not permitted with such materials. Removal of toxic materials, odor removal, very high temperatures can be used to deactivate and deodorize. Special heat recovery economizers used. Oxygen contents usually held at 4% through the combustion at the heater. So some comments about that. Where were we? I think we were here. Furthermore, direct or complete deactivation and deodorizing event volume is achieved around 780, 800 degrees centigrade. Recovery of this heat is done by the economizer built in the heater, into the heater. Economizer preheats and combusts the air, part of the recycled medium. Okay. Normally, inlet drying temperature dryer is lower than the desired or the required heater temperature. Recycled drying medium bypassing the heater section is achieved to achieve the drying temperature. So you have some sort of, by bypassing, they mean feed forward, right? The exit temperature of a heater can be quite high, whereas the inlet temperature to the spray dryer is likely to be lower than the exit heater temperature. So you need some sort of bypassing stream to reduce the heater temperature down to the temperature necessary for the spray dryer. Okay, so this is when I was saying that the complicated system. So if I go back up to this thing, this heater here may be running very hot. I may feed forward some of this flow around here to put it in this stream, and then I'd probably have some sort of mixer. So I have the hot gases and the cool gases, and that way I have the high exit temperature of the heater, which has to be lived with, but then I dilute it down to make the inlet temperature to the dryer controllable. In fact, that stream, bypass stream, would be quite useful in controlling the inlet temperature to the spray dryer. Lots of neat things that can be done. Again, the inlet drying temperature is lower than the heater temperature, exit heater temperature. Now, fermentation of pharmaceutical systems, well, there are flow diagrams for those. They're quite complicated to explain. For products, pharmaceuticals, pesticides, dyestuffs, other applications appear since designs protect the environment. Typical environmental hazards, powder emissions to the atmosphere, odor emissions to the atmosphere, powder air explosions or fire hazards, toxic or active material emissions to the atmosphere. So we got nasty stuff coming into the atmosphere. Designs prevent hazards from exiting the dryer. Typically, you pass material through a flame at high temperatures. That takes care of a lot of stuff. Okay. Typically, two-stage layouts. So all the designs that we've covered are one stage, capable of producing the desired product quality, satisfactory particle size distribution, residual moisture, and bulk density. Okay, hopefully. Obviously, one-stage dryers represent the majority of spray dryers in operation today. But there you go. There's a need for improved product quality, increased thermal efficiencies. So increases in the number and complexity of products have occurred. Time specifications have also become more difficult. You don't want the material in the dryer too long. It may change the taste, the texture, the flavor, the odor. In other words, we were talking about toxic odors or toxicity. Just the reverse of that is you want a certain fragrance, or you want a certain flavor. You don't want it in there too long because you may lose those more delicate properties that are desirable in your product. So the retention time should be kept really low here, right? So overall, that's what the time specifications. Overall, it is more difficult to dry with only one stage. So there we go. When this occurs, difficulty in drying with one stage, two-stage dryers should be used. The combination is spray dryers followed by a fluid bed. Here's some designs. Now, what I have run across with spray beds, where you have the spray dryer up here and then a fluidized bed at the bottom of the spray dryer, and they're called spray beds. Now, there are advantages and disadvantages. When I have them separated like this, I can control this part of the system independent of changes in this system. If I had a spray bed, if I changed the spray characteristics, I immediately upset the spray bed. By keeping them separate, that does not happen. So over here we have a 3A, stationary bed, back mix plug flow design. I don't know what they mean plug flow when they say fluid bed. That's interesting. Back mixed is well understood with fluid bed, but stationary. Vibrating fluid bed over here. You have vibrators. Fluid bed cyclones are for, here you have a heater. This is indicating a heat exchanger. This is also indicating a heat exchanger of some sort. I may be heating the gas. Anyway, go through here. So the reason why you would have a spray dryer followed by a fluidized bed is that fluidized beds instasize your material. In other words, you'll make a very fine particle up here, and what you want to do is agglomerate them, okay, or cause them to agglomerate. So this fluid bed may actually have a binder spray in it, and which glues particles together, but not. And the bed itself has enough agitation that the particle size reaches a certain size, and that's it. And you've glued a number of particles together that are highly porous in structure, and that's highly desirable for instantization. You're going to have stuff that's instantized. It dissolves quickly. So one two-stage dryer design attaches fluid bed to the spray dryer. Two types, well, there's a lot of types of fluidized beds, but the ones that are listed here. And again, the concept of spray beds, spray beds would be put the fluidized bed inside the dryer, spray dryer, so you have a spray bed. Now, the reason for that is you eliminate all the costs, capital costs involved, or you reduce them down substantially with a spray bed. However, as I said earlier, the sensitivities of operating two different systems, i.e. spray, dryer, and fluid bed together in one same unit can be quite cumbersome. Now, again, I've talked to several people about this, and one chap says, oh, it's terrible, so sensitive, you can't get any, it can only be run at there's one fixed set of conditions and nothing more. And you hope to pray you're at those conditions because it's extremely delicate. Another person says, hey, it's the best thing since sliced bread. So, Anyway, you have different people giving you different evaluations on the same piece of equipment. It could be due to the fact that their applications are different, but anyway. Two-stage drying is helpful. Low residual moisture content in the particle, lower particle temperatures, changes the particle size distribution, either by classification or agglomeration, improves thermal efficiencies. Spray dryers can't do everything. There you go. Spray dryers can't do everything. You can't, low residual moisture, dry to less than 0.1%, cannot be achieved in a spray dryer. Long residence times are needed. Obtaining an external fluid bed, achieving low moisture content usually requires bone dry air or relatively low humidity. By the way, the air, you might realize air is filthy, right? So you might want to filter your air. You might even dehumidify your air. We'll talk about those effects a little later. Powder may be cooled to a certain temperature prior to packing or storage. Fluid bed cooler is just the equipment for that. Effective continuous, it's used for powder temperatures above 50 degrees at centigrade. For lower, if you want powder temperatures below 50 degrees, the conditioned air may be required. Powder temperatures are the lowest in co-current dryers. Okay. Improved powder form may happen through classification or agglomeration. If you're going to classify something, you probably want a certain fraction and you recycle the rest of it. Agglomeration is kind of tricky, but it's, you should listen to my courses on agglomeration. I have 3 different agglomeration videos. Classification, fluid bed velocities can be adjusted to control fines carry-off. Removal of fines can be returned in a drying chamber for re-agglomeration, reslurring, or collected separately. Fine, I always like this. Fines may be used in re-agglomeration, right? Take the fines, it has nothing to do with drying. You take them to another process and you agglomerate them, and you may have a new product. Spray dryers operate at a low outlet temperature to obtain moisture in the product. The moisture can be used, can make an agglomerate in a spray drier afterwards in a fluid bed. It's dry on the outside, wet on the inside. The moisture will migrate out and help to agglomerate the powders. Fluidized beds are excellent agglomerators. As one chap said, performing agglomeration that cannot be obtained by other methods, and this is the idea of instantizing what that means is it dissolves really quickly. So there's a concern about drying rate, or dissolution rate, I should say. Fines are out of control, however, they can be agglomerated. Thermal efficiencies improve with additional equipment, and temperature drops. Higher inlet temperatures lead to product degradation. Lower outlet temperatures increase residual moisture. So you're looking for higher inlet and lower exit temperatures in two-stage drying, improves thermal efficiencies, no loss of quality in the product, increase in capacity of the dryer. New developments, I already talked about this. Spray beds, fluidized bed inside a spray dryer. Saves on cost and having two separate units, looks good on paper. KISS principle is violated. Keep it simple. KISS principle, keep it simple. You do not want complexity. In operations in industry, they want to be simple operations, everything's simple steps. That way you will have fewer processing problems. Maybe very touchy to operate. When you have a spray bed, right, you tend to lack nimbleness, flexibility, robustness, right? Aseptic design, basically drying a product under extremely clean conditions. Product is free from contamination, foreign matter, basically made possible through the use of high temperature Hepa filters, high efficiency particulate air filters, sterilized liquid filters, and contaminant-free atomization and discharge. Hepa filters everywhere. So we have up here, we have a sterilized filter. Got to figure out that is, and whether it's sterile or not. You have a bad stream coming in, and the question is it sterile? Is it sterile when it leaves? Of course, I got a story to tell you. The operator, one of the operators, cartridge filter, he had 50 or 150 cartridges to put in this cartridge filter. He got tired of doing it. And so next time he changed out the filter cartridges, he put in only 149 cartridges instead of they required 150. He didn't have to change out the filters anymore, and nobody ever noticed, right? So I'm sure that should not be encouraged, but it does happen, right? So we have a Hepa filter here. This is 6. That's a heater. 5A is the Hepa. 5A is a pre-filter atomizing air, 2-fluid nozzle. A. What? 5B is pre-filter dry air. Got to worry about how they filter that. And 7 is the Hepa filters. Here we go, and here we go. They're filtering after the heat exchanger. All right, filtering after heat exchanger. So you have the feed, dry product. 8, what's 8? Clean room for packing. Six are indirect heaters, indirect air heaters. No combustion products. Indirect heaters are probably required. Hepa filters, filtering the streams, making sure the X is protected. Pretty well covered it all. Every stream has been, this Q here is leaving, so that's not much of a problem. Hopefully Q resembles two-fluid atomizer. You have air going up here. Problem is you don't have a high-pressure air. Oftentimes, in two-fluid nozzles, you need the air or gas to liquid flow rates to be 2. That's just a rule of thumb. It would appear to be 2 from the technical data. I mean, if it was 0.1, the air wouldn't have any effect whatsoever. Right? But if it's 2, 3, 10, then the air will have an effect. Okay, but you have 2 sources of air here, which means 2 sources of contamination. What's this 5B? Okay. Anyway, special cooling designs used for heat-sensitive products, thermoplastics, hydroscopic materials, and materials having low softening points. Used for products, softening points. Used for products that have a tendency to form deposits on a dryer wall. Heavy deposits can mean lengthy residence times and possible degradation of quality. Fines return. Fines are out of control. It's a very famous statement. For control, fines are returned to the process. Promotes agglomeration since the process products often exhibit self-binding characteristics. Leads to production of coarser and free-flowing powders, often dust-free. So here's the 3 methods. 1, fines, you shoot it right up into the atomizer. Atomizer's discharging. This will, by the way, if this is a wheel atomizer, it's moving a whole bunch of air as well. So the fines will go possibly in the airstream. Okay, you could inject fines right in the perimeter of the atomizer again. Or the fines go in the bottom down here. Inject them at the bottom. Okay, 3 ways. Blows fines up under the atomizer wheel. This avoids the possibility of fines entering hot air where product degradation occurs. Introduce the fines to the chamber ceiling. Return the fines to the base of the drying chamber. Agglomeration may occur later in fluid beds. In other words, right here, these fines have to go out the bottom. And by the fact that they're inside this fluid bed, which may be at higher temperatures, they may agglomerate or catch on to larger particles, piggyback larger particles. Okay, some effects of operating variables. Close attention should be paid to atomization, spray air contacting, evaporation, and product air separation. Biggies. Each operation affects the properties of product to some degree. Atomization feed characteristics or feed properties have effects on particle size distribution, bulk density, appearance, moisture, and other properties, right? The ones that are non-measurable. Spray contact evaporation effects on bulk density, appearance, moisture, friability, aroma, flavor, texture, other non-measurable quantities. Again, spray air contacting. Effects on bulk density, appearance, moisture, friability, aroma, and other flavors. Okay, product separation affects particle attrition and fines. So important variables are summarized below. Be careful, these are generalizations. Anyway. Okay, product air separation affects particle attrition and fines. Important variables are summarized below. Be careful, these are generalizations. Atomization energy and operating variables. Increasing energy, rotational speed, nozzle pressure, ALR, or air to liquid ratio, or gas to liquid ratio, and two fluid nozzles will mostly decrease particle size, but at some point diminishing returns occur. The shape of the particle size distribution may not change much. Producing greater amounts of fines may form a product of higher bulk density. Again, the smaller particles may well be more dense than the larger ones, and the smaller particles may fill the voids between larger particles. Increases in feed viscosity, increases in solids. Feed solids, a reduction in feed temperature will produce coarser particles. Surface tension doesn't change much in value but often controls the final particle or drop size, the Weber number effect. Low viscosity materials, typically making drops, it's a Weber number effect. Drop diameter is proportional Weber number to minus 5.6 power or minus 0.5 power. An increase in feed solids increases bulk density. Increasing feed rate produces coarser particles. Okay, higher the feed rate, coarser the particles. Rotary and nozzles have different, let's go to the next slide. Patterns, both are flexible and can produce sprays of similar characteristics. Generally, rotaries produce finer particles, nozzles produce coarser particles. All right, let's move on down here. Okay, rotaries are preferred for large drying requirements. Nozzles require duplication, repeated nozzles. So instead of one nozzle, you'll be looking at a nozzle header with many, many nozzles, which complicates things a bit. Of course, rotaries are complicated by the fact that they have a 360-degree flat spray coming off, which needs to be bent. Okay, nozzles require duplication to meet larger spray requirements, drying requirements. Many spray nozzles can be altered by changing the vane design on wheels. That means you have to buy another wheel. That ain't good. Anyway, number, height, width, length of vanes determine the amount of liquid at the point of atomization. Okay. Airflow rates control to some extent the residence time of the product in the drying chamber. An increase in residence time leads to a greater reduction in moisture content. Okay, that makes sense. All this makes relatively interesting. The outcomes seem reasonable. Reduce air velocities help protect product recovery from drying chamber. Help product recovery from drying chambers. Airflow rate in part determines how the product is being handled and the properties of the product. Well, if the air is causing particle attrition and attrition is going to produce a lot of fines, then more gentler air, quote, gentler air, or whatever that actually means, you're looking for bigger particles, less attrition. Inlet drying temperatures increase in inlet dryer temperatures increase the drying capacity of the dryer. No, that's true. Higher inlet temperatures lead to higher efficiencies. Increased temperatures cause higher evaporation rates and often cause a reduction in bulk density. Higher evaporation leads to more porous particles, faster evaporation, more bubbling, so to speak, sort of like the molasses analogy. Higher evaporation rates cause more porous and fragmented particles. Outlet drying temperature should be kept in a narrow range to maintain powder packing and flow requirements. Increasing outlet temperature decreases moisture content. Okay. Also means more airflow rate, probably. Lower outlet temperatures produce a powder high in moisture content, which may be needed in subsequent agglomeration processes, such as incidentization. Ancillary equipment may be needed to handle high moisture powders. And spray drying followed by fluidized bed is a natural fit. Other dryers may also follow a spray dryer as well. For example, belt dryer. These combinations have been less studied. Anyway, let's go on to some wheel effects. Wheel designs, atomizer, pumping, air pumping, and spray and air contacting. Wheels are going around at extremely high RPM, and they pump a lot of air. That's one of the first things we got to state right now. The amount of air is large, very large. Anyway. Wheel designs, numerous designs are available. Designs to have a design that imparts a product with a desirable desirable characteristics. Standard wheel design, straight vanes, usually 18 to 36 vanes, cheap to fabricate, no special liquid distribution techniques, clog-free. Air pumping in the rectangular or oval channels, that's a problem. The air or gas will aerate your feed. You're no longer feeding a liquid stream on the wheel, but you're feeding foam on the wheel. Nozzle atomizer wheel, small diameter orifices instead of channels. Air pumping is substantially reduced. Less flow area, higher the density. Yeah, product aeration is minimized, which is a good sign. And this is highest possible bulk density. Usually you're after high bulk densities. You do not want low bulk densities, basically, because of packing. If you're shipping 20 pounds in a cubic foot, that's pretty low packing, right? A low density. We go back and catch that. You have wheel, nozzle, atomizer, wheel. Okay. Allows only relatively small feed rates. Okay, vane wheels are used over straight vanes, used for higher bulk density and higher production. Densifies the product. Occurs as the feed approaches the channel exit. You're looking at 7 to 10% increase in bulk densities over straight vanes. Occluded air and product is reduced. Important in products containing fat, whole milk is an example. Steam wheels. Steam flows alongside the wheels, alongside feed in the wheels. Replaces air around the wheels. Steam minimizes particle expansion during initial stages of drying or the initial stages of boiling. Results in higher bulk densities. You can actually form more solid particles. Effective for products that exhibit film forming characteristics. You put a pot on the stove, pot of milk on the stove, and heat it. You'll produce a film on top of the milk, just to give you an idea of something that forms a film. Steam reduces air pumping. Okay, wheels for corrosive feed. Fabricate the wheel from corrosive resistance metal, hastolate and titanium. Vane wheels for abrasive feeds, well, significant wear or erosion occurs at 10 to 20 meters. You can put that in your memory bank. That means 30 feet to 60 feet a second. One solution is use wear-resistant inserts. Wear plates inserts are replaceable, obviously. Other abrasive designs, wear-resistant cindered bushings. Used in de-aeration also are used here. 24 bushings per wheel is not uncommon. Bushings are rotated after significant wear. And bushings can be made of all sorts of stuff, right? Solid wear liners created from the feed itself, basically. oftentimes the way you create a liner for some vessel or whatever is you let the feed build up on it for a while. During the startup of dry spraying are also used. Large capacity wheels use double tier or more wheel designs. Each level is fed by a distributor. Use multiple levels. Liquid loading on each vane is kept low. Complete atomization occurs at high feed rates. Possible problem is wheels flooding. Ooh, that's often an interesting point. If, say, you had suddenly a massive buildup of your material on your wheel, it's not, flow channels are significantly reduced, wheel will become flooded. That's kind of an interesting idea. Where feed rate is larger than the amount of atomized. So you have the amount of atomized, but the feed rate's larger than that. Designs to prevent flooding is a vendor question. Anyway, here's a tip. I took these pictures from Nairo, I think. Appreciate their contribution. I think these have bushing. This is an indication of bushing. Okay, a bushing. Some other wheels indicate bushings in there. Right. Double decker there. These look like they're hot. Anyway, by hot, I mean there's information on them. Disc atomization, vaneless bowls, cups, and plates. Well, you got to recognize that at the perimeter here of these discs and things, they're direct drop production, big drops. A few daughters, but big drops. They can also have ligaments coming off, very uniform ligaments. It's how cotton candy is made. It's how party string is made. There's no breakup. And the liquid can come off as a liquid sheet. Now, again, if you're atomizing a slurry, I'm always interested in the particle size versus the drop size in atomization of slurries. I'm quite sure there's a solid, what is it, the diameter of the solid to the diameter of the drop becomes important. In some slurries, it can be considered a homogeneous liquid. In other slurries, they can't. And then you have particle shape effects, where you suddenly have flat plates lining up with each other, or needles lining up with each other. So anyway, again, I encourage you to look with my video on atomization. And the feed rate, disc diameter, and rotational speed, that goes back. There's calculations for when drops are produced, when ligaments are produced, or when sheets are formed. Basically, it's fed inside a bowl, pressed against the bowl, flows outward to the edge of the bowl. Plates can also be used. Difference between plates and cups is the cone angle. Plates have 180 degrees. Bowls and cups less so. I'm going to give you an example. This is 380. This is 360 degrees, and then if you have one of these, the angle would come off, however dictated by the geometry. Disc atomization, little use in commercial spray drying operations. Well, this really depends upon whether you want a uniform drop size or not. If you want to, this one right here, ligaments, give you uniform drop size. Okay. And for some commercial applications, uniform drop size is equivalent to a lot of money. Okay. I've been around several companies where they're seeking 10 micron drops plus or minus 1 micron, very sharp distributions. And they have reasons for that. Anyway, so, well, it depends, right? Little use in commercial spray drying operate well. It depends upon what commercial means. Often applied for coarse particles at high production rates. Multi-tiered plates are used for high-capacity dryers. Used in special applications. Can be used for coarse, fairly homogeneous sprays. Problems with abrasion will occur. Fan spray patterns may not have not been used to any large degree in spray drying. Now, having said that, I suspect that somebody out there uses flat sprays. Flat sprays can let you zone your dryer, spray dryer. You have, say, a square box or square rectangle. You have flat sprays, flat sprays, flat spray. Anyway, every time you say it's not used, somebody will pop up with an application that uses it. And there will be some advantage that they cite as being the reason for why they use it. So that's the way industry is. There's a whole variety of different things that actually work. All right. Hollow cones are well suited for co-current operations. Spray cones can readily align itself with co-current flow. Drops readily contact the drying air when they're flowing in the same direction. So sprays from solid cone nozzles have less interaction. Okay. Solid cones are useful for countercurrent operations where the spray meets the full face of the drying air. When a hollow cone sprays contact countercurrent air, a greater degree wall deposits may occur. All right. Hollow cone in contact with countercurrent upward air expand out the cone angle, unfortunately. Would increase more flow to the wall. And obviously, this is a small chamber effect, especially in small chambers. You got to worry about size effects here. Small chamber, you're always going to have serious wall buildup problems. Problems aren't important unless you have them. All right, mixed flow chambers, if solid sees co-current first, use hollow cones. The spray sees countercurrent first, use a solid cone. Right. Okay. Anyway, advantages of two fluid nozzles. I was in Europe giving this course. And the chap came up to me and he said, the biggest trend in industry is two fluid nozzles. And I said, okay. And he was disappointed in my response that I did not thoroughly agree with him. I agree with most everybody because most everybody is often right, right, to a degree. So, you know, two fluid nozzles, big trend, okay? Let's talk about it. Produces spray of high uniformity, high homogenization, small drop size. This is true if the second fluid, the fluid that's doing the atomizing, is doing a good job. If the gas to liquid ratio is not high enough, what you have is dripping. Okay, I ran across a petroleum company that was using a, how can I put it, plant-made or homemade two-fluid atomizer, burning off their nasties in a combustion chamber. And the nasties had a dripping component to them. There was a puddle of nasty stuff right below the atomizer. So it was a two-fluid atomizer. It's doing a great job, except for the fact that whatever reason, the thing dripped. And if you have a low gas to liquid ratio, then the gas is ineffective and your atomization depends upon the liquid stream. And the liquid stream may not be up to snuff, so to speak, up to the abilities of doing its own atomization. Okay. Usually have large orifices for feed. There's two types of two fluids, internal and external. These are nozzles, of course. Internal mixed and external mixed. Internal mixed has a problem where one stream may back up into another stream. That ain't healthy. Does not need a high-pressure feed pump. That's true. What it needs is a high-pressure gas pump. That's what it needs. The high pressure's got to be available. You're not relying on the liquid to do the atomization, i.e., you're not relying on the feed to do the atomization. You're relying on the gas to be doing the atomization. What I really like are two fluid atomizers. You have them everywhere in the petrochemical industry. They're not called two fluid atomization or atomizers. They're called flash drums. You have this huge pressure drop across an orifice of hydrocarbons, and they basically flash off the low hydrocarbon, and the heavies stick around with big old drops. Anyway, flash drums. Another really kick about two fluid atomizers is instead of worrying about pressure, right, a high pressure drop, you run it boiling. In other words, your flash drum runs boiling, right? You put the gas in there, or you put two liquids in there, and you heat up. One of the liquids has a boiling point, lower boiling point, and it will be the one that flashes as it goes through the orifice. So you heat it up under pressure, above its boiling point, push it through the orifice, and voila, you have one heck of an atomizer, I'll tell you. Forget about pumps, forget about high pressures. Well, you got to worry about back pressures if the thing's going to atomize. You want to obviously have the flow go out the orifice. So you have enough pressure to prevent the backflash might be considered. Anyway, these two fluid nozzles are, well, they sell them, right? Okay, and it's two fluid atomizers, but there's a lot of homemade two fluid atomizers out there that are not called atomizers. Okay. You put two liquids through an orifice, then you heat them before going through, and you heat one you heat the liquid, the two-phase liquid above the boiling point of one of those phases. You got one hellacious atomizer. Disadvantages: two fluid atomizers usually have small annuli or orifices for gas stream. More tendency for plugging. By the way, all the disadvantages here, obviously, may or may not be significant, right? Need filtered compressed air or clean steam. Again, you have steam and you have stream. Obviously, you can atomize with whatever you want. Steam is not uncommon. That's available too, and it's already got a lot of energy into it. High cost of an air compressor, high cost of producing atomized air, heating requirements for atomized air. Cold atomizer air reduces evaporative cooling capabilities as much as 20%, low nozzle efficiencies. But this whole area of two fluid nozzles are kind of cool because there's a lot of different techniques and strategies you might want to go about, especially if you run boiling through an atomizer. Two fluid rotating cup atomizers, rotating cup with air direction at the rim. Contains a very fine spray, low viscosity, atomizes high viscosity coarse drops. Okay, spray angles may be small. Can be duplicated for larger dryers. Disadvantages of two fluid rotating atomizers, the same as two fluid nozzle atomizers, right? Or the same advantages as well. If you run boiling, it'd be quite interesting. Selection of an atomizer, well, simple construction, easy maintenance. That leaves out wheels. Sorry. Wheels require delicate, if they're rotating at 40,000 RPM, you just don't pick a person off the street to do the maintenance. You know what I mean? Wheel right, balance the wheel. You use a wheel balancer. Again, I suggest you review the course on atomization. Various available in various sizes. Of course, that's what you're looking for. Particle size control through changes in operating conditions. Operated using standard feeding equipment. Atomizers suitable for operational flexibility. Handles wear. Drop release is compatible to dryer chamber. Right? Spray pattern compatible to dryer chamber. Atomizer provides complete atomization. Power requirements are reasonable. Again, power requirements, very important. Pressure drop times, volumetric flow rate. Pressure drop. If I have a nozzle, it's a pressure drop across the nozzle, not in the piping system, across the nozzle, times volumetric flow rate is the power requirement or power being used by that nozzle. Similar calculations can be done with wheels. Power is central to engineering and should always be calculated for your equipment. And I assure you, or I would guess, that you haven't calculated the power requirement or the power of wheels, right? Which would be some sort of rho v squared, right, times volumetric flow rate, rho density velocity squared, volumetric flow rate, might plus. You check your units. Units are your friends. Anyway, additional comments. Rotary and nozzle provide all capacity requirements at low, intermediate, and high flow rates. Okay, it's good. Got a lot of versatility. Rotary atomizers are better at high capacities. Okay. Nozzles reach duplication, high capacities at duplication. Okay. Power requirements are the same order of magnitude. Power rarely determines atomizer selection. You need to do the power calculations, though, just so you don't remain ignorant. Apologize for that. I'm sure nobody's ignorant anymore in the world. Nozzle efficiency is rarely important if nozzle is successful. I mean, if you got a working system, then don't fight it, you know. I've always pondered people improving the wheel. They wanted more roundness to a wheel. By the way, trying to obtain more roundness to a wheel is, stop to think about it. Drop size distributions are similar at low and intermediate flow rates. Yeah, Weber number effects. Maximum, minimum drop sizes are selection criteria. Fine sprays, you have these atomizers. Intermediate sizes, you have these atomizers. Coarse sizes, pressure nozzles, vane discs. Fine sprays, I would go with a cup atomizer. You want to essentially create a mist. And again, ligament, I would try to have a uniform drop size around 50 microns probably for very fine sprays. And I would be looking for, if I was to try to incorporate that in a liquid, I would want to have it catching mechanism, falling liquid curtain to catch the material. Rotary atomizers are more flexible, often just changing the wheel speed. Nozzles are more adaptable. Basically what they mean is nozzles can be changed out, easily positioned, mixed, countercurrent, co-current are possible. Nozzles are just a hunk of metal, right? No moving parts. The pressure was generated elsewhere, right? Rotary atomizers require and generate a rotating air power. Rotary atomizers, of course, then nozzles as well, is going to generate a lot of airflow or gas flow. Low viscosity, non-corrosive, abrasive fields, wheels and nozzles have equal success. Wheels can handle corrosive, abrasive, and powder feeds. Wheels and pneumatic two-fluid nozzles can handle materials that cause pumping problems. Right? This is high pressure, high viscosity materials that cause pumping problems. Pneumatically two-fluid nozzles are used for high viscosity and non-Newtonian materials. It's useful to base atomizer selection on past experience. There you go. Lab and pilot plant experience. Atomizer selection is not an exact science. For example, if I'm spray drying milk in the US, I'll probably use a nozzle. If I'm spray drying in Europe, I'll probably use wheels. So there's no real exact science. Each atomizer field dryer combination has cases where performance suffers, hence are unsuitable. Obviously, pressure nozzles are unsuitable for slurries, fiber slurries. Nozzles will clog. Nozzles will clog below 0.3 millimeters. And they'll clog with just simply water. Water contains enough contamination at 0.3 millimeter that can easily clog. Pneumatic two-fluid nozzles should not be used for feed that cannot withstand high impact. There's high impact between the one fluid and another. And for instance, if you had protein molecules or long-chain polymer molecules or other stuff, and they might have the high pressure drop might rip apart the polymer chains. Feeds containing long-chain polymers form threads. It's interesting. Threads, veined atomizers. This is cotton candy type behavior here, right? If you look at, you got an assignment I want you to do. I want you to go buy some cotton candy, and I want you to see how uniform those threads are and the sugar fibers that make up cotton candy. Then I want you to go to the carnival where the cotton candy is made, and I want you to watch the high-speed rotating cup that they make cotton candy from. Then I want you to figure out the diameter of the threads in cotton candy. And then I want you to figure out what the controlling parameter is between making threads and making drops. And I suspect it may be something to do with higher viscosities as you approach the drying of candy, of sugar water. If you're drying sugar water, you're going to approach higher viscosities because the sugar concentration goes up and up and up. All kinds of cool stuff you can do. And retrofit selections based upon what fits the existing design. Ah, yes. Retrofits. Oftentimes, whatever the design was for a plant, it's been changed. It's been changed by a retrofit. And if that didn't work out, it's been changed again to another retrofit. So plants often undergo changes, and rather dramatic changes, especially when they're not working. And the idea of retrofits is very common. There is no such thing as a fixed process. You're always looking for ways of getting better performance. The dryer chamber determines the atomizer. The position of inlet and exit air ducts often determines the atomizer. Dryer chamber determines the atomizer. If you have a tower dryer used nozzles before, then the new atomizer will use nozzles. So we collapse all this stuff down. What do we got? We quickly find that comment on atomizer selection. Not often a clear-cut choice. Often done by the elimination of poorer choices. There you go, poorer choices. You're playing in this process Sherlock Holmes, so to speak. Air pumping effects. We'll take a short break here and resume. Okay, let's talk a little bit about air pumping effects. First off, little is known. Okay, little is understood. Energy going to pumping air can be high relative to energy going to atomization. So there's an there's an energy difference there. Air pumping can aerate the fluid or can aerate the liquid in the atomizer. The feed then becomes a foam, which can affect product quality. Obviously, a foam feed will reduce bulk density, or probably will reduce bulk density. And wheel design can help reduce the aeration effects. So the wheel air pumping effects and spray drying air mixing near the wheel, right? Affects the spray air contacting or mixing near the wheel. This mixing effect appears in pilot scale equipment or where the distance from the wheel to the wall is small. Air pumping and liquid inlet air can interact and form recirculation flows that can cause material deposits on the walls. Step to minimizing air pumping, better designs. Minimum clearances between the wheels and casings. Wheel designs to minimize aeration. Bleed cold air into the wheel casing clearances. Fill in the recirculation volumes. Well, that may not be a great idea. Take that back. Spray air contact, very important. It determines the rate of drying, the extent of drying. Spray shape, chamber, air dispersing designs must create a flow pattern which prevents wall deposits. Many dryer designs and interdependencies, no general relationships are available. The amount of published literature is limited. Most are about small dryers. Fine sprays move under complete influence of the air. Coarse sprays are more independent of the airflow. Correct air dispersing stands out as an essential requirement for successful spray drying. That's probably true. And again, this is where the spray drying companies, the vendors, come in handy. And we have here we have air coming in, countercurrent air leaving. These are more or less pictures of co-current and countercurrent operations. Here we have a rotary disperser right below the slurry feed. Here we have a vane ring gas disperser. The air comes in tangentially and goes around the ring. Here we have spray nozzles inside. We have the gas coming alongside those spray nozzles. Two fluid pneumatic spray nozzle dryers. Anyway, so we have, these are from Master's book. So just took those. Thank you I thank Masters for this knowledge. Inlet sealing volute, air rotation by angled vanes. Cone angle is bent to match the chamber, air and spray. Anyway, you have the hot air coming in through vanes up here, or vanes are actually in the cone. And you want enough air, if this is a horizontal spray, you want enough air to bend the spray. You have sealing vanes, upper wall volute. Here you have a volute up here. Hot air in as a tangential flow, probably. That would prevent hot or cold air in. You have hot air coming through the vanes. Tangential air in, flow rotates in the chamber. Again, the cone angle is bent to the chamber. Okay. One of the interesting comments that was once made, they had spray nozzle or spray wheel below a entry region. And due to a back circulation, the entry region draft tube or tube, basically a large diameter tube, and then the wheel set just below that tangent, that inlet tube. There was a back circulation, and the back circulation caused buildup of material on that tube. It had a huge inlet tube duct, basically wall circulation caused buildup along the outside perimeter of that tube. And the way you solve the problem is you just go in and cut off the portion there the buildup occurred. Oh, but that will ruin the warranty. Well, which do you want? A process which has a wall buildup in there substantially, or do you want one that is not under warranty and doesn't have the wall buildup? Here we have a center air disperser, comes in here. Rotation controlled by angled vanes and rotates in the chamber. So of the three, A and B are better than C. C has the potential of having more wall buildup material. See, in this here, the air is bending the flow. Here, the air is coming in, bending the flow downward. Here, the air is going upward, or may have an upward component to it. It doesn't bend the cone, the spray downward, but it may actually bend it up in the reverse direction. So then it's more likely to have wall buildup here and here, since the opportunity of bending the spray angle has been missed. So has the advantage of inlet hot air going right to the spray. There you go. Co-current, air and wheel discharge rotating in the same direction. You have more control. Right. Countercurrent, discharge, more mixing. Wall impingement more often decreases. I was going to say actually increases, but more decrease may often. Greater tendency of material to build up on the surface of the atomizer. Here we have a couple more. Here we have a Plumen 1, 2, 3, basically. Here we have a perforated sheet, straightening vanes, perforated sheets as well. Perforated sheets, straightening vanes are used to prevent air is dispersed across the cross-section. What you want to have, well, you got to decide what you want to have. But one thing is often a choice is have uniform air. Have uniform air, you need probably to have some pressure drop across the sheet. In fluidized beds, typically you're looking for to get uniform airflow through a fluidized bed. You want 1/3 the pressure drop across the support grid. Here, I'm not sure exactly how I get uniform throw, but I want maybe even targeted flow. Maybe I don't want anything at the wall, but a lot in to bend the liquid angle there. Let's catch what I set up there. Okay, covered that. Here I would have wall disperser, tangential or volute inlet hot air, central disperser here. Wall bristle dispersion, another one, horizontal vanes, one vertical vanes. Bustle type are commonly used, bristle or Brussels. And again, we have sealing or base dispersers depending upon nozzle location. Here we have D. B is a fountain type. And I guess we have to think that this is also a fountain type. All these are sort of fountain types, so they're all inverted to gravity, but A is not. Anyway, it doesn't hurt to do visual studies using a small plastic model to gain some sort of information. Now, what size do you go to? Well, I bought a plexiglass tank that was 3 foot in diameter. It cost me $900 at the time. You just take a sheet of plastic and bend it over and seal it. You can gain a lot of information, possibly, using plastic models. I would expect the vendors already have their plastic models. But the idea would be you have all sorts of ways of putting in air and all sorts of geometries. And you put in the problem would be the surface would become opaque after startup. So you run it empty, you run it just with plain air. You could run it with confetti in there to be flow markers. That way you could see on the inside what the different flow patterns are and how they change. And you do it on a relatively large scale. Like I said, 3 feet in diameter would probably be a nice size to understand things. And then the flow markers, you would, you obviously can't use the particles themselves because you wouldn't be able to see in. So you use confetti, low concentrations of confetti. Maybe you can see what happens. The old common statement is a picture is worth 1,000 words. And if you have a video, you have lots and lots of pictures. So you gain understanding. The idea of a confetti air circulation in a tank, you make the tank such that you have this large cylindrical tank and then you have inserts to give you, say, a slanted wall. Dispersive air around the nozzle leads to faster drying rates, better utilization of chamber volume. Lots of interesting combinations. But if you notice this presentation, this is the area of weakness in spray drying. Really, it is. And hence the weakness in the presentation. No, I did my best on a hard subject, Anyway, I'm just kidding. Operating effects and effects on dry product properties. Effects depend upon product drying characteristics. Particle size is controlled by wheel speed for wheels. High feed rates may result in higher residual moisture content and higher bulk density. Increased feed temperatures may increase bulk density, improve atomization. Decrease bulk densities for easy atomizable feeds. Right, so increase, decrease, may deaerate the feed and increase bulk density. When it says improve atomization, what that means is smaller drop size. Bulk densities increase upon powder cooling. It's interesting. Again, I want you to do my experiment. There's an experiment I want you to do. I want you to take some ground coffee in one of those, the big coffee cans you see, about a foot or 10 inches in diameter, maybe 10 inches high. And I want you to empty out the coffee grounds. You buy it new, filled up totally. You empty out about 50% of the coffee grounds. You put the top, measure the height off the bottom. Put the top on the coffee ground can, plastic top usually, and then rotate it, rotate it around and around and around and around. And then after about 10 to 20 revolutions, you put it down on the countertop, take the lid off, and I want you to notice the height change that's occurred due to the tumbling action, right? So that's a comment on bulk density. Here I have a can of coffee under one set of bulk densities. And then if I rotate it, by the rotation, I probably increase the static charge on the particles. Hence, they have a tendency to expand away from each other. Hence, I have a lower bulk density. Now, I don't know whether you live in a humid climate or not, but suppose you're dry, it's dry on the inside, you're in an air conditioning, and that usually means drier. And I want you to do the same trick and expand it out amount of coffee in your coffee can. And then I measure the heights, and then I want you to put it outside where you have high humidity. And notice what happens after a while. As the humidity diffuses into the coffee, the static charge is shorted out, so to speak, because of the moisture. And the coffee tends to collapse. So this business about a moving stream and electrical charge, you need to pay attention to that. Not only could possibly kill you, it also will affect your bulk densities. Okay, so lots of people have died of static charge, just charges. Whenever you have anything moving, you'll have a static charge, potential static charge buildup. That's how electrical generators work. Basically, if something moving, it sucks charge. Anyway, case in point, this is in a chemistry laboratory. The director of research walked into this organic chemistry lab, and there was a crackling sound. And the director asked the chemist what that sound was, and the chemist said that he didn't really know. And so the director of chemistry walked over and turned the lights off. And there was this plastic pipe that was lit up like a fluorescent light tube. And it was lit up with tiny sparks. And it was a plastic pipe with benzene running through it. So you can imagine all they needed was to have the end of that plastic pipe exposed to an oxygen source, and away you go. It would not necessarily be a pretty sight. Okay. Let's see, where were we? Powder from rotary atomizers usually have a higher bulk density than the powder from nozzles. Bulk density depends upon particle size. Bulk density also depends upon particle shape, depends upon particle charge, electrostatics. It depends upon, obviously, lots of things. Flowability depends in part upon particle size. Powder bulk density depends upon packing. Upon packing depends in part upon particle size distribution. Wider distributions have higher bulk densities, smaller particle sizes fitting in between larger particle sizes, hence higher bulk densities. Increase in feed solids, increase bulk density. There you go. There are exceptions. Feed aeration decreases bulk density. Spraying foam for very porous particles is possible. In other words, if you want very porous particles, then you definitely want to spray foam. Suspension to give you higher bulk densities in solutions. Interesting, due to the mechanism of drying. Increasing moisture content increases bulk density. Okay. Wheels that reduce air pumping increases bulk density. Replacing air within a wheel with steam. Now this is steam injection around the atomizer. Increases bulk density. The injection of steam will slow down the boiling to some degree, and it won't be as foamy as the boiling molasses analogy. So it's slowing it down. That means there would be more solids. Less foaming means lower diameters, same solids, lower diameters. Increasing inlet air temperature decreases bulk density. Reducing outlet air temperature increases residual moisture content and increases bulk density. Contacting where the wettest drops meet the hottest air minimizes bulk density. So this would be co-current dryer. Again, your hot air causes the boiling, bubbling, and as a result, see, the drops aren't evaporating. They're really doing a phase change. The moisture is not really evaporating in the sense of hot vapor coming off a cup of coffee, but instead it's more like boiling from the vapor coming off a boiling situation with liquid pot of water on the stove. Big difference between a cup of coffee cooling down and boiling water on the stove. High countercurrent drying increases bulk density. Mechanical handling causes attrition and increases bulk density. Reduction in static charge increases bulk density. Static electricity is something that is not very many people are accustomed to or talk about, so you need to pay attention to this. Additional tricks to increase bulk density. Add a binding agent. This improves the particle strength, reduces or prevents ballooning. I guess that means boiling during evaporation. This probably came from Master's book. Ballooning, I'm not sure. I guess they mean boiling. During evaporation allows the operations at higher solids content. Injecting steam, we've mentioned already, replaces air and increases bulk density by 30%. Drops have less colluted air. I would say included air. I would say occluded. Feed, pre-crystallized feed solution as a cold suspension, pumpable suspension, can decrease bulk density. Okay. Interesting, just as a comment, pressure swirl nozzle has centrifugal force inside of it. This pressure swirl, because of the swirling action, you have significant potentially demixing going on in your flow in a pressure swirl nozzle. So portions of your leaving liquid sheet, one side will be high solids and the interior side will be just liquids. So the concentration in a spray, you're assuming it's all the same concentration. May not be all the same concentration. There may be a concentration difference in a hollow cone nozzle, for example, between the outer portions of the sheet and the inner portions of the sheet. And that's kind of a cool thing to see if it happens. Demixing often occurs when you don't pay attention to it. Drops reach their boiling points, and a semi-impervious surface layer forms. Moisture puffs out the droplet, and the droplet expands. This is the idea of molasses boiling. Evaporation, moisture evaporates faster than the diffusion of solids back into the particle. Voids are formed. Liquid and solid flows to the surface by capillary action. Forms a void near the particle center. Weak point in atomization is wall deposits. Majority of spray dryer users consider wall deposits the most important disadvantage of spray drying. The reasons for wall deposits: Atomizer air dispersers, flow maldistribution, Atomizers, and Atomizers discharge momentum and direction, which is essentially number 2, flow maldistribution. Reasons are combined and overlapped. Flow maldistributions and air dispersers go in one side of the chamber, causing a backflow on the other side. Flow is not uniform across the disperser. Major problems with imbalance flows causes significant localized wall deposits. I was talking to a young lady in Amsterdam, and I asked her how thick her wall deposits were, and she said there was a ring around where the wheel atomizer had worked, and the ring was 3 inches thick. Well, she said it 5 centimeters thick. It was distributed, right? High in the center and low on either side. Very symmetrical. Flow rates can cause undeveloped sprays or poor spray symmetry. Sprays a mist so fine that it becomes suspended in the air. Mist gets away. So there is no wall buildup if you have a mist, very little. If it does, it occurs as a dust, if any. However, if the dust is electrostatic and the charge attracts it to the wall, so you have an electrostatic effect perhaps. Lots of reasons for poor symmetry. Poor surface finish in the nozzle, orifice of wheel imperfections, plugging and fouling of material buildup, contaminated flow passages, non-uniform material sprayed. Material needs to be filtered to remove lumps, all right? If lumps are one side of the nozzle or the wheel. Eccentric alignment of nozzles, right? Pressure swirl, chamber and orifice is not aligned. What's really cool about, there's a company that makes spray nozzles in the United States called Spraying Systems. They have a really fantastic videos on the different ways of nozzle wear. And it's pretty funny how much industry does not pay any attention to nozzle maintenance. Anyway, distribution from rotary atomizers are more difficult to measure. Here we have spray nozzle. This is good. This is out of Lefebvre. Lefebvre is a book I primarily used for the atomization course. Okay, so you may go back to the atomization course. And you can see a maldistribution. See, on one side, this one goes up right in here and down on this side. So they have a bad situation on this side. The way you get rid of that is, or I understand that, is you go with a padnator, collection of test tubes, spray, and the various test tubes will tell you which part of the spray was collected. And I'll just run through some of these. It should be obvious, right? So we have this situation going on. So we have that, we have that, we have that. Areas of likely wall impingement of dry product. 3 modes of wall buildup: wet, semi-wet deposits caused by coarse droplets not having sufficient time to evaporate. Sticky deposits by the nature of the material and temperature, or surface dustings. Large drops, wet, semi-wet deposits caused by large drops in spray and incomplete atomization. Occurs in areas where the droplet have a direct path from the atomizer to the wall, which is almost everywhere. Right. Again, you want to bend the cone angle with air. Can break off as wet lumps or streams flowing down the wall. Not a good situation. Eliminate deposits require change in atomization operation. Drying air has little influence. If that much has happened, then you got to change the operation, put in better baffling or better air direction. Sticky solids occur over the entire chamber. Occurs when the material contacts the wall. Many of these deposits build up to a certain thickness and fall off. Surface dusting occurs when material contacts the wall. Dusting does not form hard layers, can be easily removed with an air hose or air knife or light brushing. Dust depends upon wall geometry, wall cleanliness, local velocities, electrostatic forces. Retention on the material on the walls. Not desirable over lengthy time intervals. Material may affect product quality, may become scorched or mixed with others. Product causing contamination, leads to an unsealable product, contributes to frequent cleaning, more frequent cleaning. Hard layers are difficult to remove. If they're difficult to remove, you just leave them there. and you now have a new wall. Loose production due to extended shutdown times for cleaning loose production. Anyway, the idea of putting a surface contaminant, okay, wall buildup is due to agglomeration, period. Whatever mechanism. So you're going to do, to prevent wall buildup, you prevent agglomeration. One way of preventing agglomeration is you use a surface poison. Common examples of surface poisons is bakers will put powdered sugar on donuts, and that prevents agglomeration of donuts. Cookies are often coated with granular sugar, or also powdered sugar. Hard candy at Christmas time are separate pieces. But in February, they've all fused together, agglomerated. So oftentimes, holiday candies like that are coated with a powdery substance. Salt. If you buy salt at the store, it has another ingredient in there that surface contaminates the salt to prevent it from agglomerating. Clear plastic wrap has a very thin layer of silica on its surface that prevents plastic layers like Glad wrap from clinging, or from, they still cling, right, but keep them from fusing together. So it is possible that if you have substantial wall buildup, it may help by wall poisoning, so to speak. And the way you get information on that is basically through experimentation, for one, or reading the literature on agglomeration. Agglomeration is quite desirable in many, many processes. However, it's also undesirable in lots and lots of processes. Anyway, most dryers operate without material on the wall. Other dryers operate with material on the wall, where the material requires limit retention time on the wall to complete drying. Okay. That way it's not a problem, and hopefully it'll come off the wall. These materials offer greater resistance to moisture evaporation. Residence times of 5 minutes may be required to obtain a dry powder. Well, that's kind of interesting. You have it stuck to the wall, and after 5 minutes, it's eventually dried, and off it comes. Example includes fruit and vegetable powders. Products sprayed in this way form porous agglomerates on the wall. Thickness builds up to a certain level, then the material breaks away to form nodules. Degradation of products can easily occur, and need for continual removal of the wall, removal of the material from the wall. Wall cooling may have an effect. You may actually want to operate this way, where you may run for 5 minutes, have the stuff build up, have it dry out, and then you go with the wall scraper and scrape it down. All right. I'm not saying it's a good thing, but I'm saying it may lead to the product built up on the wall. You scrape it off, you have your product there. It may be quite sellable. So what you once called a waste stream, by the way, that's an inappropriate term to use, waste. Things are no longer wastes, they're just byproduct streams, right? You gotta get with the program, so to speak. Never declare anything a waste. It's a byproduct. I mean, what can I say? Anyway, it might lead to a different product for you. Never underestimate the ability of the American public to buy strange stuff. I mean, it amazes me what people will purchase. I mean, and think, you know, cutting edge here. I don't know. Just as a social comment, I apologize if I offended any of you. Wall dependent deposits occur more frequently in smaller dryers, of course. The radial distance to the wall is smaller. Little data available concerning wall impingement. In fact, you could say have a falling Well, you may want to spray to get rid of the initial moisture, and then you have a wall, hits a wall, and then the wall, it's inclined, so the material flows down the wall, becomes your product. Small chambers. Deposits often occur at levels of atomizing wheels. That makes sense. Semi-wet deposits have been reported for small co-current dryers with rotary atomizers. Okay. Spray rakes can collect impingement profiles. You go in with a patinator. Instead of collecting the liquid, you collect up impingement material. So you get an idea of the amount being sprayed at that moment on the wall. Variations in wheel speed, feed rate, atomizer location can affect the degree of impingement. Impingement area. Impingement moves around. It's interesting. Occurs on the ceiling, agitated level, atomizer level, and below the atomizer level. Small chambers at low flow rate. Increase in wheel speed decreases sealing impingement, increases impingement below the wheel level. At higher flow rates, maximum spray density can occur at roof level, dryer roof level. That's interesting. In some cases, a secondary area of heavy deposits form. So, kind of interesting. Where was I? In a fountain type dryer, large drops fall out of the air and onto the cone in the dryer. Okay. As these drops fall, they pick up smaller ones and drier particles. Heavy cone deposits often occur. So what we're talking about, say this right here. You could potentially have substantial wall buildup and ceiling buildup here, and you can have sprays coming down and not drying well, and by the time it gets down here, you have a problem. Large chambers, wall deposits easily controlled and less likely. There you go, the reason for big stuff. So you have a scale-up issue here. Small scale, you'll have wall buildup, and that may have prevented you from continuing on with the scale-up process. At large chambers, the effect would not even be apparent. Things change with size. You got to be aware that certain physics occur on the small scale, certain physics occur on the large scale, and they may not be the same. Okay. Large chambers, wall deposits are easier to control and less likely. Longer airborne resistance times for droplet. Longer airborne residence times for droplet drying. Droplet travel is controlled by air velocity and direction, controlled by adjusting air dispersers, and scale up the problem of wall deposits may disappear. Co-current, rotary atomizers, sealing air dispensers. Gas rotation controls spray dispersion, forms an umbrella-shaped spray cloud, eliminates wet, semi-wet deposits. Co-current dryers, nozzles with non-rotary air dispersers, limited adjustments possible. From perforated sheet or straightening vanes, control is limited by using a disperser. Nozzle positioning is flexible. Slight repositioning can direct a spray away from the areas of wall impingement. There's a smart move, right? You'd be able to have nozzles that have some sort of directionality to them. Nozzles and clusters centrally located within a rotary air disperser have the wide range of impingement controls. There you go. That makes sense. Centrally located in a rotary air dispenser or a rotating air have a wide range of impingement controls. Again, we have this situation occurring. In here we have a air broom. I always thought these things were flimsy, but maybe they work quite effectively. Who knows? For the vast majority of products, powder will not adhere to the wall if dried properly. Once drying is over, chamber is cleaned, air is swept. Vibrators on the wall help. Air broom systems are available. Secondary air source along the wall can help. Air knives, basically. Sticky products are likely to have wall deposits irrespective of the flow pattern. Deposit-free operations depend upon drying characteristics of a particular material. And in some cases, the elimination of impingement position can be done by streamlining the drying chamber. Fill in the corners. Wall deposits are a big issue. This may indicate that a spray dryer may not be the best dryer design. And we'll stop here.